Right. One of the important property that you may get out of stress strain diagram is ductility, right? Ductility, we all know, is a measure of the material's ability to deform, right, under loads. So how can you quantify, okay, ductility for a material? When I say what is the ductility of aluminum, we can always say aluminum is more ductile than steel, but when I ask you to quantify, what is the way out to actually give out some name and say, okay, this is this much percentage, or this is these many times higher, more ductile than steel or something like that. So the idea is to quantify ductility. So what is the way? It is again from the stress strain diagram. So what we do is we have change in length of the specimen of the test piece, right? By the time it fracture, it will be elongating to some extent, right? So the ductility can be given as the percentage elongation, okay? It isn't it, right? That is nothing but ductility. And of course, either we can quantify it by using the change in length or the change in diameter, okay? If you carefully see, it elongates in the length direction, and not only that, it is accompanied by the reduction in the cross sectional area, right? So now we can easily quantify it either by seeing the what is the percentage, okay, elongation or the percentage reduction in the area, okay. If I give you say this is the initial length and this is the final length, you should be able to give the ductility in terms of percentage of elongation. Similarly, if I give you the initial cross sectional area and the final cross sectional area, should be in a position to calculate the ductility based on its change in the or the reduction in the cross sectional area by using either this formula for elongation or this formula for area reduction, okay, right. If you see the diagram here, you can now clearly see a brittle material is actually having very less elongation, right, or the less ductility, simply because if you see the change in dimension, the percentage of elongation or the reduction in the area, reduction in the cross sectional area, it will be much lesser for a brittle material, whereas for the ductile material, you see it has elongated so much from A to C, and if you actually calculate, the ductility will be much more compared to the brittle material. And this is a schematic material, how a brittle material typically translates into a stress strain diagram, its behavior, and similarly for a ductile material. Incidentally, you can see the strength or the tensile strength, if you see, that is higher for a brittle material, okay. For example, your ceramics, okay, or the steels which have a high strength and so on, whereas the ductile materials, mild steel, okay, or the aluminum and so on, they have very good ductility, and you see that translates into this the more the portion of the horizontal curve, okay. Of course, the strength, if you see, the strength is highest, or the tensile strength is definitely lesser than a brittle material or the stiffer material. The other important measure for mechanical behavior, to understand the mechanical behavior of any material, okay, is hardness, okay. The hardness of a material is a mechanical property of any material, okay, and it is it gives a sense of, okay, a feel of the strength of that particular material, okay. It actually represents how much of tensile strength a material may possess, okay. It's a rough estimate. When two materials, if you take one, out of which one material is having higher hardness, you can also safely assume that is also having higher strength, okay. And of course, there are many reasons why hardness test is so popular, okay. Some of the reasons that are given here are, for example, the test is so simple and inexpensive. You would have already experienced this in your laboratory when you try to do measure the test, okay, the hardness of any material, right. So the test is so simple that all that you do is take the specimen, a proper specimen, right, and try to indent, okay, it with a suitable indenter, okay. Based on the type of indenter and the type of load, we name it whether it is a Brinell hardness, whether it is a Vickers hardness, okay, whether it is Rockwell hardness, okay. There are different tests that we will come to that, but basically it is very simple test and very inexpensive in nature, okay, because the same sample you can use again and again, and you can conduct different indents altogether, and you finally come up with average value. Okay. So now, what are the other advantages of hardness test? So basically, you can consider it as a non-destructive test. Okay, though you are actually modifying the geometry of the material by large, so you can consider this as a semi non-destructive test. Okay, because if you take the tensile test, okay, where you are actually breaking or fracturing the sample and it becomes useless, right? So whereas in many other tests like impact test, torsion test, in all these cases you are actually breaking the material and which becomes useless for any other purpose. Okay, you cannot be using that particular specimen in the functional applications. But whereas hardness test you can always conduct on a material that is actually functioning, or you are actually on a material that is put into application. Okay, that is why we may call it a non-destructive, okay, type of test, though you are actually locally deforming the material, right? Yeah. What is the other important advantage? It can actually give an estimate of the strength of the material, okay, the strength properties, okay, as I said earlier. Okay, and now finally, how can you define hardness of a material? You can actually define the hardness of a material is its resistance to the localized deformation, localized plastic deformation. Okay, you should be very precise. Okay, and of course, people also say it is the resistance for scratch. Okay, that means its ability to resist the scratch. Okay, that means localized deformation. Again, scratch is nothing but. Okay, so all these definitions hold good, and the basic understanding that you have to have is that it is basically the resistance for localized deformation, the two plastic deformation. Okay, right. And of course, based on the function, based on the type of material you want to test for the hardness, you actually go for different type of hardness tests, starting from the Binel hardness test, where you may be using a steel or tungsten carbide sphere, okay, of 10 mm diameter, for example. Okay, and of course you have a formula, okay, after indenting, for example, using this indenter, a spherical indenter, you have a diameter, right, diameter of the indent. Okay, and then if capital D is the diameter and this P is nothing but the load, actually how much load you would have applied during the test, you can actually calculate the Binel hardness number, okay, using this simple formula. And if you may be wondering how this formula, we are arrived at this formula, you can check any of the literature where they would have given a proper derivation to have actually to arrive at this particular relation between the hardness number and this load and the diameter of the indent. Okay, right. If you see the Vickers hardness, okay, again we use here not the spherical one, but actually a diamond pyramid type indent. Okay, that is why when you see the indent, it looks like in a diamond shape. Okay, and you have again a relation between the Vickers number and the load and actually the diagonal. Okay, if you assume it is a symmetric one, the whatever the impression that you have, okay, that indent, then you have the diagonal to be some say D1, then it would be the relation between Vickers hardness number and the load that you would have applied and the diagonal of the indent. You have this relation. All these relations you may remember, so that it is easy for you whenever you conduct any hardness test readily, just by measuring the diagonal or the indent diameter and so on, you can measure the number without depending on the instrument and instrument software. Okay. Similarly, you have Knoop micro hardness, whereas again you have a diamond pyramid type indent. Only thing is the angle would differ. Okay, for example, here you have 136 degrees angle of the pyramid, whereas you have another one called Rockwell and superficial Rockwell, where you have a diamond cone sphere. Okay, where you have the angle to be 120 degrees Celsius degrees, and of course again you can apply here different loads like this. Okay, you have different scales of this Rockwell. Okay, so based on that, again you will be measuring the hardness. So all these different tests actually are intended for different type of materials. For example, if you take Vickers, okay, for the softer materials, typically we use Vickers hardness, say aluminum, okay. So it is like that. Yeah, so coming to the next one, which is a very important topic, okay, which we call the fracture of metals, okay. It is very important to learn about the fracture of metals, because many a times you see that materials fail by fracture, right? When you conduct a tensile test, ultimately how the material is failing? The material is failing by fracture, right? Because the material is getting separated into two pieces, right? How it is happening? Is it happening suddenly or gradually? For example, you can assume small minute cracks that would have initiated within the material at a particular point, okay. These minute cracks, micron sized cracks, okay, slowly get accumulated, and finally the effective cross sectional area gets reduced because of these voids, okay, and finally there will be a critical cross sectional area beyond which, okay, the material can no longer bear the load, rather it succumbs or it yields to the fracture, okay. That means it will the cracks, micron sized cracks now get propagated at a much larger pace, and you actually see a sudden failure, a fracture surface being formed, okay. That means you will have now new surface being formed in the form of fracture, right. So now this fracture can be thought of as 2-3 different types of fractures, okay. For example, if you see here on the left hand side A, if you have this kind of fracture, okay, specimens after fracturing, if you see at the fracture is here and you see there is a tip, that means the material has deformed so much before fracture, okay. It can be considered as the ductile fracture, okay. Similarly, if you see here, it is a moderately ductile fracture, because you have sufficient deformation that took place before actually the fracturing the material. Similarly, you can consider this type of fracture to be brittle, because you have no previous indication that actually material may be failing somewhere. It is altogether sudden, okay, or apparently you have no clue where the fracture is going on, because there is no necking taking place, right. So this kind of fracture we call brittle fracture. All these are possible cases. If you take typically ductile materials, you will see this kind of fracture happening. If you take moderately ductile, you will see like this. If you take brittle materials like ceramic and so on, like brick for example, you see this kind of fracture, isn't it? Right. And this is a beautiful micrograph or the photograph actually of the fractured surface of a ductile material here and a brittle material here. Okay, if you see the ductile material, you see there is an appreciable deformation, okay, you see before actually it fractures, right. And this is the counterpart of it, and you can see actually this looks like a cup, right, this part of the fracture surface, whereas this part of the fracture surface looks like a cone. So that is why this kind of ductile fracture is also nicknamed as cupped cone fracture or cup and cone type of fracture. Okay, whereas the other scenario, you have brittle fracture where you don't see any appreciable deformation before fracture, and you see the material is very intact until the last moment of the fracture. You see only fracture surface you see, and it is very gentle and flat, right. So now just by seeing the fracture surface, you can infer many things, okay, about the kind of fracture, kind of material behavior, okay, and so on. That is why we actually take the micrographs of this fractured surface, okay. That means you put it under the microscope and see the microstructure, and we call them fractograms, okay, like the way we call micrographs when you take the normal surface. And from these fractographs you can actually infer many information about the material's behavior, how its microstructure is, and how or what is the cause for the fracture, where the crack initiated, where the initial nucleation of the crack happened. All these things can be inferred from this surface, okay. That is actually very much required, because you can understand why the material has failed, okay. In many of the consultancy work, many people investigate how the crack actually initiated and propagated, especially in aeronautical components and so on.